In this topic, in this video, we will be learning about delta modulation. This is also called DM. Delta modulation. And this is also called 1-bit DPCM. Why? You will understand. Wait. In delta modulation, first point is transmission bandwidth is less when compared to PCM as well as DPCM. So the transmission bandwidth requirement of delta modulation is less when compared to PCM and DPCM. To get this transmission bandwidth less, N value is taken as very small as possible and is considered as 1 bit per sample. So always in delta modulation, whether they mentioned or not, we should know that N value, small n value is 1. So 1 bit per sample. So small n value is 1 in always delta modulation. So it is also as 1 bit. Why DPCM? I will tell you. Similar to DPCM. Why this 1K means n value 1. What is the transmission bandwidth formula? Transmission bandwidth or minimum transmission bandwidth is RB by 2. RB is NFS by 2. That is nothing but Fs by 2. Are you getting my point? Here n value is 1. So RB equal to NFS. So RB and Fs both are same. What is RB called, sir? RB is called bit rate. What is Fs? Fs is called sampling rate. So bit rate, sampling rate all are same. Also equal to students pulse rate. Pulse rate means the number of pulses per. Here we are using 1 pulse per 1 bit. So number of pulses, number of bits also same. If n value is 1, then what is L, sir? L is 2 power n. That is 2. Means in delta modulation, we are using 1 bit quantizer. So that's why we can also say delta modulation complex is less when compared to PCM and DPCM. PCM and DPCM not 1 bit quantizer, some n bit quantizer, but here in delta modulation 1 bit quantizer. That is also having, I will give you clarity, having only 2 levels. One is plus delta level, another one is minus delta level. Plus delta level given to the encoder, it will generate 1 bit. Minus delta level is given to the encoder, it will generate 0 bit. When plus delta, when minus delta, I will tell you, wait. But it is having only 2 levels. Follow. What is happening in delta modulation is, students, let's take a simple example, one beautiful example to understand the delta modulation. Suppose you are staying with your friend. Now listen, you are staying with your friend. Now listen. You seen your friend today. Now cases will follow. Case 1, you are seeing tomorrow. Case 2, you are seeing after 5 years. You seen your friend today. First case, you are seeing tomorrow. Second case, you are seeing after 5 years. In which case the differences will be more? Obviously in the second case. Why? The time gap is more. Means the difference between the successive samples are very, very less because the time gap is small. Here, what we are doing in delta modulation is we are taking the difference between present minus previous sample. That is going to be quantized. But in DPCM, we are taking the difference between actual sample and predicted sample. But here, present sample and previous sample. If that difference, whatever be the amount, if that difference is positive, quantizer will round up to plus delta level, encoder will give you 1 bit. If the difference is negative, quantizer will round off to minus delta level, encoder will give you 0. Delta means step size. That value, some value will fix. How to fix that value, I will tell you, wait. So finally in delta modulation, what we are doing, sir? We are taking the difference between present and previous sample. Let's see the delta modulator transmitter block. And then also I will take you an example to explain how the process is going on. If I take the delta modulator transmitter block, sampler, before that low pass filter common. So the first block is sampler. For the sampler, we are giving our message. Message is m of t. What is the sampler will do? Sampler will give you the samples that we are calling as a present. So m of nts. This is the present sample. What we are coming from here is, let's take m bar of nts, that is called previous sample. That is called previous sample. That difference we are taking and giving to the quantizer. That is going to be giving to the encoder. Output is DM signal. And this quantizer is 1 bit quantizer. What we are having here is the delay circuit. Delayed by TS. This is in the feedback path. This is the circuit diagram of course, the block diagram of a delta modulation transmitter block. Here, what we are quantizing, sir? Let's take the error is E of NTS. Here the error E of NTS is nothing but the present sample M of NTS minus the previous sample M bar of NTS. For example, if I take the quantizer output is EQ of NTS, if I draw the graph between EQ of NTS versus E of NTS, the transfer characteristics also we can say the input output of a system. If E of NTS is positive, plus delta, negative, minus delta. That is the transfer characteristics of the quantizer here. Now I will take you an example. I will show you how this is going on. Means I will take one example of the message. Just follow. You can wait here itself. I can take. So what I am doing is I will take one practical message and how the process of the delta modulation is going on. I will show you. Means if you give the M of t, how that DM signal is coming, I will show you here. For example, I have a message M of t equal to, let me take one pulse. So I am taking one sine pulse. For example, this is our M of t. Where is this is given to the sampler? What is the sampler output? Is M of NTS. What is the sampler will give you? Sampler will give you the samples. For example, the sampling rate is, if you take some TS, this is NTS. Let's take for example This is TS. This is 2TS. This is 3TS, 4TS, and 5TS. That is the sampling intervals. Now follow. At T equal TS, we got the first sample, 2TS second sample, 3TS third sample, 4TS fourth sample, 5TS fifth sample, like M of NTS will come. That is given where at summer we given, summer output is nothing but E of NTS. What is E of NTS, sir? E of NTS is the difference between present and previous. Just now the operation started, nothing is there in the delay. There is no previous sample, means you can feel as 0 volt. This minus 0 volt, this amplitude, whatever may be, you can orally you can see. This amplitude minus previous amplitude, difference positive or negative? Positive. Next, this sample will come, this will be coming as a previous sample. This minus this, present minus previous, as positive. Now this is a sample, this minus this, positive. Now this is the present sample, this minus this, negative. This minus this, negative. Like error E of NTS will be generated. This is given where the quantizer output is EQ of NTS. Positive means plus delta, positive means plus delta, positive means plus delta, negative means minus delta. And all these are given where, sir? Encoder. Output of the encoder is nothing but our delta modulated signal. Follow. Plus delta means encoder will give 1 bit. Minus plus delta means 1, 1, 0, 0. For example, 1 we are representing with the positive pulses, 0 with the negative pulses. That is the delta modulated signal generated from the generated for this corresponding message. Now this is going to be transmitted through the channel in the receiver side. From here, we will generate this message back. This is the transmission block and this is the process of generation of DM signal. Clear? Yeah. Now see the delta modulator receiver block. Just now we see transmitter block. And for this message, I generated the DM signal. Now by taking this DM signal, we need to reconstruct this M of T at the receiver end. What is the last block in transmitter, sir? Encoder. So here, first block is decoder. What is the input of the decoder? The generated DM signal. Next we are having summer. Output is given to the low pass filter. It will reconstruct M of T back. Same here also we are having delay, delayed by 1 bit. Here TV, TS all are same. This is the circuit diagram or block diagram of delta modulated receiver. What is the delta modulated signal generated? 11100. So if plus delta given to encoder 1 bit, 1 bit is given to the decoder, it will generate plus delta. I am writing that summer output. Summer output as well as low pass filter input both are same at T equal to TS. Summer output or low pass filter input both are same. At T equal TS, first bit came 1. 1 means decoder output is plus delta. Just now operation is started, so nothing will be there in the delay. So output is delta. Now that delta is going to the low pass filter as well as now storing in the delay. Try to understand. What is the summer output at T equal to 2TS? What is coming? 1. 1 means plus delta. What is there? Also delta. So 2 delta. 2 delta given to low pass filter, stored in the delay. What is the summer output at a t equal to 3ts? Coming is 1, so plus delta, previously 2, so 3 delta. Same 3 delta given to low pass filter as well as stored in the delay. What is the summer output at t equal to 4ts? Coming is 0, so minus delta, previously 3, so 2 delta. What is the summer output at t equal to 5ts? Coming is 0, minus delta, previously 2, so delta. So finally, what is the low pass filter inputs? That is nothing but summer output. Are you following my point? At t equal to ts, delta. Delta means some amplitude. How to set I will tell you. Next at t equal to 2ts, 2 delta, 2ts time. At t equal to 3ts, 3 delta. At 4ts, also 2 delta. At 5ts is delta. That is the low pass filter input. What is the low pass filter output? I am writing with the black color one. What is the low pass filter will do? Will charge it to those samples. So smoothly connecting these things. That is the low pass filter output. Now you can see we are able to reconstruct the original message what we are transmitted. Maybe writing mistakes means exact representation maybe in the hands it will be there. But if you take the exact value of step size, we can reconstruct the signal exactly same as the original message what we transmitted. So this is the receiver block. Are you getting my point? Now we will see the conditions. What is the condition for delta to reconstruct the original message signal exactly back? That delta value itself is called ideal value of delta, or you can call as a exact value of delta, or that is also called optimum value of delta. That is also denoted with delta OPT. If I take this optimum value of delta, exactly I can reconstruct the original message signal. What is the condition we have up to now? Or what is the constraint or what is the condition? The reconstructed signal shape should be same as the original message signal. The reconstructed signal shape should be same as the original message. Now you can think about what is the condition to make two signal shapes are same, or more clearly I will tell you what is the condition that two curves are having same shape or two lines are having same shape. Think about that and see the next video. Clear? Yeah. Hello students, in this video we will be learning about the conditions for optimum value of delta, slope overload and granular error. Yeah, in the previous video itself I given a hint. So if I take exact value of delta, that is called optimum value of delta, that is denoted with delta OPT, then we can reconstruct the original message exactly back. And what is the condition we have? The reconstructed signal shape should be same as the original message. The reconstructed signal shape should be same as the original message. What is the condition that two signals will have the same shape or two curves are having the same shape? Yeah, their slope value should be same. How to calculate the slope of a continuous time signal? Differentiate, you will get a slope. Integrate, you will get area. What is the slope of a reconstructed signal? Slope means y by x, change in y by change in x. That is nothing but delta by ts. This delta itself is called delta optimum. This is the first condition we got. This is for optimum value of step size for general message. Later I will also bring for sinusoidal message. Now follow. Sometimes maybe chosen value of delta greater than optimum, or maybe chosen value of delta less than optimum. Greater than optimum means you will also get error, less than also will get error. This is called granular error. This is called slope overload error. Very, very, very important. The questions in the delta modulation means they will come from granular error or maybe from slope overload error. First put the heading granular error. When granular error is coming, sir, whenever chosen value of delta greater than delta optimum. Divide both sides by Ts. So delta by Ts greater than delta optimum by Ts. That is delta by Ts greater than delta optimum by Ts means from here d by dt of m of t. This is the condition for signals are having granular error. Granular error having another name also idling error. Idling error. So let's carefully listen these points. Granular errors will come whenever chosen value of step size greater than the optimum value. Granular errors will come whenever the slope of a reconstructed signal greater than the slope of a original message. To reduce the granular error, we need to decrease the step size. Why? Already choosing more, so error is coming. If you want to reduce granular error, delta value should be decreases. What is the condition to avoid granular error? Greater than is to have the error, then less than or equal to will be to avoid. This is to avoid, this is to have opposite condition I written. Now what about the slope overload error? Let's see. When slope overload error will come, sir? Whenever delta is less than delta optimum. That is delta by Ts less than delta optimum by Ts. From expression 1, delta by Ts is less than delta optimum by Ts means d by dt of m of t. This is a condition that signals are having slope overload error. You can treat this is the condition 2, this is the condition 3. Slope overload errors will come whenever chosen value of step size less than the optimum value of step size. Slope overload errors will come the chosen slope of a reconstructed signal less than the slope of a original message. To reduce the slope overload error, increase the delta because already we are choosing low. To avoid the slope overload, what is the condition? Greater than or equal to. These are the 3 conditions we got for general message. Now I will bring another 3 conditions for sinusoidal message. Follow. Sinusoidal means let us assume message m of t equal to am cos 2 pi fmt or maybe am sin 2 pi fmt. Bring delta optimum by Ts. I am taking maximum value and that to modulus. So positive value. What is that? D by dt of m of t. Differentiate am 2 pi fm minus sin 2 pi fmt. let's take the modulus. So finally, let's take the maximum condition, maximum value. Delta opt by Ts equal to 2 pi Am Fm, maximum value of that sine itself is 1. This is the condition for calculation of optimum value for sinusoidal signal. Let's take this the condition number 4. Now what about the condition for granular error and slope overload error? Granular error means delta by Ts greater than 2 pi Am Fm. This is for granular error. Delta by Ts, this value I substituted there. What about for the slope overload error? Delta by Ts less than 2 pi Am Fm. This is for slope overload. This is for granular error. This is for slope overload error. Just d by dt of m of t I written 2 pi Am Fm. What about to avoid? Exactly opposite. This is greater than, less than or equal to, you have to write. This is less than, greater than or equal to, you have to write. These are the total 6 conditions. 3 for general message, another 3 I given for sinusoidal message. Clear? Yeah.